Well, hello, everyone. Hello. Welcome to our live stream chat for AP Statistics. Getting a bit of a feedback there. Okay. Are you hearing this?
You need to turn off your volume, I think.
Okay. That sounds fine. How about this?
That's better. Can you hear me?
Yes.
Okay.
I apologize to everyone who is watching that. So anyway, welcome to our live chat, AP Statistics Review. And my name is James Bush. I teach mathematics at Waynesburg University. That is south of Pittsburgh, Pennsylvania, where it snowed this morning. Yikes. But anyway, I teach mathematics, statistics. I'm also a 14-year AP Statistics reader. I know the ropes in terms of the scoring rubrics, and I am here working together with Karen Knight, who I will introduce in a minute, to take you through the AP Statistics exam review. So let me introduce Karen Knight. Karen is from South Lake Carroll High School in South Lake, Texas. Karen, tell us a little bit something about yourself.
First of all, I'm going to give a shout out to all of my kids who are logged on here. I miss you guys. Y'all just found out about this about an hour and a half ago. So thank you for stopping whatever you were doing and coming to join us. Yes, I have just finished, or I'm finishing my 26th year of teaching and have been an AP reader, not quite as long as James has, or Mr. Bush. I've been AP reader for, this will be my 6th year. So Mr. Bush is fantastic. He is one of the stat gods, and you're going to really learn a lot. So I teach AP Calculus as well. I've taught that for about 20 years or so. So I'm really missing my classroom right now. Didn't really know I would ever say that, but I'm really missing it. So.
I think we're all missing our students and classrooms. All right, this is going to be very interesting because every time I talk, I'm getting this feedback. So that's okay. I've got my hand on the button. When I talk, I just have to turn it down. When I don't talk, I turn it up. All right, we'll deal. We'll deal. So we're going to share a PowerPoint slide, set of PowerPoint slides with you.
Mr. Bush, hang on just a second. Do you by any chance have another tab open that is the streaming?
I do not.
Nor do I.
Okay.
They're saying the echo is still there. Maybe another tab with the stream open.
Oh, got it. All right. Okay, I see.
Hi, Rahul. Hi, Sachi.
Lost. Okay. All right.
No other tab where it's open?
How about that?
That is still doing it.
Yeah.
Okay, I would say just turn it down then.
How about that?
Still there a little.
Okay.
All right, he's going to join us back on. Sorry, guys, we weren't getting this feedback when he was talking to just me. All right, let's see. Let me see if I can find him again. Where did he go? All right, we appreciate y'all's patience. For my own students, okay, yes, I did re-invite him. For my own students, you know what happens because this is so like me in technology, something is going to be an issue. Okay, let's try that again. What we have to say is really, really great, though. So y'all are really going to enjoy this once we get our technology working. Okay. Okay. Tejas, I keep inviting him. And are you sure you want to invite him? Yes, I do. Keeps popping up.
Okay.
Okay, now you're back. Hi. All right, James, can you hear me?
I can hear you.
Perfect. And we do not have that echo.
Very good.
Good. All right.
All right,
now,
we apologize for that. As I said, we tried our best to get all the technical glitches out of there beforehand. But all right, I'm on, Karen's on. Can we pull up the PowerPoints?
Yes.
And I suggest once we get there, we will stay there.
Yeah, we probably don't need to go back and forth. Okay. I'm ready.
Okay. Now there's also one last problem on my end, is that
okay, why does he keep going?
All right, let me adjust my volume. And I think we're good to go.
Okay.
All right. So welcome to our NMSI AP Reader chat. Once again, James Bush, Karen Knight, Pittsburgh to Texas, snowing in Pittsburgh, probably nice in Texas. Let's take a look at our slides and what we've prepared for you today. Okay. All right, Karen, are you able to go to the next slide there?
I think I can.
All right. Sounds good. Yeah, some rules here, just some housekeeping rules. We're going to chat with each other, so be nice. You're going to meet other students, and you're going to ask some questions to clarify some concepts in AP statistics. You can ask questions in what we call the parking lot. You can post any questions you have. You can give a thumbs up to other questions or comment on questions that you can help with. Let's be helpful. We're all going to try to be helpful today. Answer other people's questions, post good resources, and share tips and tricks. That's what we're going to do. Right? We're going to share some tips and tricks and common errors. Let's get right to it, shall we? Okay. So, once again, some factual information. The 2020 AP Statistics exam is Friday, May 22nd, 1 week later than it would ordinarily be. And the interesting part is it's 2:00 p.m. Eastern time. That's like Pittsburgh, New York time here. So, wow, just imagine this exam, of course, is international. So I'll let you guys do the math on what it takes for the Beijing people to take this exam. They'll be getting up at like 2 in the morning. I don't know. We all know the format. 2 free response questions. 2, that's it. Multiple parts though, but there are no multiple choice questions, no investigative task, no chi-square, or, now careful what I'm about to say, inference for regression, no inference for regression. And don't go off and say, oh yeah, James Bush told us there's no regression. Yeah, that's not true. That's not true. No inference for regression. Question 1 is about 55% of the exam. It's going to take 25 minutes, followed by 5 minutes to upload your response. Question 2, about 15 minutes. No, scrap the word about. It's 15 minutes, followed by 5 minutes to upload your response. Now, before we get started, I want to put in a little plug, and I'm serious. Every one of you has a really, really, really good shot at passing this thing. Now think about it. There's no pesky multiple choice questions. So for those that would always get tripped up with the arithmetic and all the probability rules, no, this is your year. We're two topics shy. No chi-square, no inference for regression. It's going to focus on the concepts of the hows and the whys and the whats and interpreting things. So really, this is your year. I mean, you might not view it as such, but I think this new exam is going to level the playing field. So hopefully you all get through it. Let's take a look at the first slide that we prepared. Okay. And of course, this is, I'm calling this Tips for the 2020 One-of-a-Kind, hopefully, AP Statistics exam. Now, the first thing, know your vocabulary and the correct use of vocabulary. And I want to start talking about confounding. So what is confounding? Okay, now a lot of books refer to confounding variables. That's fine, but it's more like you have confounding between variables. Confounding between the explanatory variable and some other variable. Now, on the AP exam, you're going to have to explain how the other variable is associated with the explanatory and is associated with the response variable. Now, one example that you see below is, it's a silly one. It's a silly one. For children in the primary grades, there is a strong positive association between the size of a kid's shoe and the size of their vocabulary. Okay, now I say, what is the potential confounding variable? But again, it's more like the shoe size. Now take a minute to think about this. Take a minute. What other variable is in play? And shoe size would be confounding with age. Age, sure. Older the kid, bigger their shoe size. Older the kid, more words they know. Age. Shoe size and age are confounding variables. They are confounding with one another. A little more serious example, a study that's predicting infant birth weight from maternal weight gain during pregnancy. Okay, predicting infant birth weight from maternal weight during pregnancy. Again, there's a strong positive association between maternal weight gain and infant birth weight. But what other variable is in play? Well, for this one, it would be the length of the pregnancy, the length of the present pregnancy. So we would say that maternal weight gain and the length of the pregnancy are confounding. So anyway, a little about confounding. Make sure you're using that properly. Make sure you understand what a confounding variable is. Stratified sample, cluster sample, and blocking. Wow, these are all very confused with one another. A stratified sample is when you classify individuals of a population into groups of similar individuals, called strata. Now, the grouping is done on a variable that you think is going to be related to the response variable. Now, cluster sampling also involves a grouping. Yeah, so it's understandable that these two are confused. But a cluster sampling, the groupings are done for convenience. Yeah, they're classify the groups of individuals that are near each other. We call them clusters. Now, as an example, what if we're sampling students from 9th to 12th grade high school? And I'm going to start with a cluster sample, okay? Perhaps I will sample some of the homerooms, okay? I'll take a simple random sample of homerooms. The homerooms are my clusters. And I've got a captive audience of maybe 20, 25, 30 students in a homeroom. I can quickly give my questionnaire, and it's very convenient. But if my response variable is some sort of an opinion, and I think that the freshmen are going to answer differently from the sophomores, from the juniors, and from the seniors, okay, and I think that the class is going to, that again, the students are going to respond differently, then I'm going to stratify. I want to take so many freshmen and so many sophomores and so many juniors and so many seniors, because I want to make sure I get the opinion of everyone, the freshmen, sophomores, juniors, seniors. So I'm creating those strata before I take the sample. Yeah, and that's the difference between the two. Karen, I'm going to let you talk about the next one, blocking.
Okay.
Blocking.
All right. Blocking. Do y'all hear an echo at this point? I'm hearing myself echo.
Oh no, you too. No, you're fine. You're fine on my end.
I don't know how to make it go away on my end. That's better?
Well,
okay. So blocking is to experiments as stratify is to sampling.
mm-hmm.
So they are basically the same thing. However, you use that concept in a different scenarios. So if you are selecting people to be part of your sample, that is when you're going to think of the word stratify. And S stratify, S with sample. Okay, I can remember that in my brain. And then if it's an experiment and you feel like, oh, in my classroom, I don't know, talk about shampoo. If you think shampoo, for example, is going to affect boys' hair differently than girls' hair, then you would block by gender so that you would not have that confounding variable of gender affecting your outcome. If you feel like it's going to be age, then you would obviously block by age. You're trying to separate to try to help control that confounding business. So an example here, an experiment is to be conducted to determine whether whether oil type affects the car's engine life. In previous studies, it was determined that engine size, a 4-cylinder, a 6-cylinder, or an 8-cylinder, is associated with engine life, but the car type, there's a coupe, a sedan, a wagon, a truck, is not associated with engine life. All right, so if you would type into the chat what you think the blocking variable is.
Is it engine life? I mean, is it in size or car type?
Or car type.
Size or car type.
You would a couple of people type into the chat what you think it is. In previous studies, it was determined that engine size is associated with engine life, but the car type is not associated with engine life. All right, so there we go. We're going to block by engine size because that's going to have an effect on the outcome as opposed to the type of the car. Okay,
Good.
Great job there. All right. One other thing you need to really focus on, and my students in here, you better know all of this, knowing that vocab, the difference between a population versus a sample. So your population, that is where you get your parameters. So that is the big picture. You take a census, 100% of your people that you're interested in. That is extremely impossible with a good study in real life. So the reason we're taking samples is to be able to get data from people that are representative of the whole population. So then you can make inferences about the population. If I have a census and every single person has responded to my question, like let's just say, for example, in my classroom, if I have a class of 35 and every single person answers my question, why would I need to get a sample to see what they would answer? So a sample is coming because you are unable to get a census. So knowing the different symbols, the mu, the p for your proportion, the standard deviation of the population, or rho, which we're not going to use in AP this year. But your samples, your survey sample, the statistic, vocab word you need to know is point estimate. And your point estimate, we know that from, it is the middle of your confidence interval is your point estimate. The halfway mark between the lowest and the highest value of your confidence interval. And that is either an X bar or a P hat. Those are your point estimates. And then a sample standard deviation is going to be S. All right.
By the way, before you leave that slide, I'm going to make the point that when I was typing up that slide, X bar if you are typing word processing this exam, okay, you can write X bar. That's fine. They'll know exactly what you mean. So if you feel the need to write X bar and are worried about, oh my, I've got to go to an equation editor, no. Just go X bar or PHAT. That will be 100% acceptable abbreviations for X bar and P hat.
Perfect.
Okay. Well, now the next section, number 2. Let's be careful with our what I call turn of phrase. And a turn of phrase, if you don't know, is a vernacular for something that's either very good, a phrase that's very good and very memorable, or pretty hideous. All right. So what I'm going to do, all right, I've written some common incorrect phrases, and I'm going to ask Karen what's wrong with what I've written. Here I am, I'm working on the AP exam, and I say, the distribution of the heights of these students is normal. That's what I'm submitting. Karen, what am I going to get for that?
Ooh, you're going to get an I, because that is too specific.
Oh, man.
So nothing is ever exact in stats. So if I say something is normal, I have to have 100% of the population.
Yeah.
So it should really be the distribution of the heights of the students is approximately normal.
Approximately normal. Wow. Okay. All right. I'm describing a distribution, and I'm heading for spread. And I say the range of the heights of these students is between 54 inches and 72 inches. That's what it is.
I know. That one sounds almost correct to me. I think it's going to be the word range. I think range applies to one numerical value, which would be the difference between 72 and 54. But
in this case, it's 18.
Yes. This one would really be the spread.
Yep. All right.
Can you stop for just a second, James? I have a question over in the chat, and it's a great question that we need to address. Could we say on the first one, the distribution of the heights of these students is approximately normal, is what we would say. They're asking, could we also say that it is symmetric?
If that's what it appears, yes. And actually, we're going to be touching on that in a little bit.
Yes.
Good question. Yeah, absolutely. Actually, let me answer that now. Sure, if you're looking at a box plot, and the box plot looks nicely symmetric, please don't say that it's normal. You cannot tell a normal distribution from a box plot. The best you can say is that the distribution is symmetric. Great question. I like it. All right.
Absolutely.
So my third bullet item, it's some sort of a regression correlation type of thing, and I'm looking at a scatter plot, and I say, oh, there is a strong positive linear correlation between the amount of sugar and the number of calories in snacks. And that's what I'm writing down.
Amount of sugar and the number of calories in snacks. Okay, is it really supposed to be a correlation?
Oh, yeah. Misuse that word. Yeah, correlation is a number. It's a number between -1 and 1. Well, in this case, it's going to be a number between 0 and 1 because we know it's positive. I use the word correlation. What should I be using?
They're nailing it over in the chat. They're telling me association or the word relationship. Wonderful.
Terrific. Yeah. Karen, you're at an advantage. You can see that chat. I cannot. So,
I'm so sorry. Okay.
No. That's great. That's great. So, awesome. Okay. How about this one? So again, doing a regression problem. The slope is 4.2. I'm here to interpret it. So I say, okay, for every 1 gram change in the amount of sugar, the calorie content increases by 4.2 calories. Obviously, some sort of a study about the relation between sugar and calories in a snack.
Correct. All right. One thing you're going to get dinged about, there's a couple of things in this that is wrong. It sounds great, but we need to tweak a few things. Okay, change. Change could mean increase or decrease. So what kind of change are you talking about?
Yeah, I was really wanting an increase. I was talking about an increase. Thought that would be good enough.
All right. So if we change that to say for every 1 gram increase in the amount of sugar, That's much better. The calorie
Right.
content increases by 4.2 calories.
That's my answer, and I'm sticking with it.
Well, now it's going to be a P.
Okay.
So when it said 1 gram change, it would now be an I. We fixed the word change. We were more specific and said which direction. But at this point, we're saying the calorie content increases by 4.2. That's an exact value. And everything with statistics is all about a prediction.
Right.
So we need it to be, it increases by a predicted 4.2 calories.
Yeah, I would probably go the predicted calorie there's a lot of ways we can fix this. The predicted calorie content increases by 4.2 calories. The on average, the calorie content increases by 4.2 calories. Yeah, a couple of ways we can fix that. Excellent. Okay. Let's move away from regression and now test of hypothesis. Okay, so this is going to be a test of a proportion, p equal 0.5, p greater than 0.5. Oh, don't forget to define your parameters. Oh, yes, parameter p, I better define it. Obviously, this is some sort of a questionnaire. Students had to answer yes or no to a certain question. And I'm going to define p as, this is a tricky one. Where p is the true proportion of students who answered yes to the question. That's the definition.
I know, that one's like fingernails on the chalkboard. Okay, it's the past tense that's wrong with that one.
Okay,
all right, answered. If you have answered the question, now that means you were part of the survey or you were part of that sample and you already answered.
Right.
But so I'm not trying to test the claim of who sampled.
Yep. So really, I should be saying, my favorite phrasing is where p is the true proportion of students who would answer yes to the question. Okay, who would answer yes. Read into it. Who would, if given the opportunity to take the little survey, answer yes to the question.
Right. Yeah. You could also, in there, Brandon is saying over here in the chat that you could say something like students like the ones in the study, which that is very true, but students like the ones in the study, yes, that would be acceptable as well.
Yes, true proportion of students like these who would answer yes to the question. So folks, you see how important our English grammar is. Wow. Did you ever think you'd be doing so much writing in a course like this? And that's what makes it fun. It is fun. And as I say, this year, in my opinion, the playing field is leveled. You know, it's less about your technical skills and more about your interpretation skills. Moving on to a test of hypothesis. Again, this is a little subtle. Okay, so I fixed the whole would thing. Okay, and here's my conclusion. Okay, let's pretend the p-value is less than 0.05, and I rejected the null hypothesis. And here's my conclusion: the true proportion of students like these who would say yes to the question is greater than 0.5. Okay, how about that for a conclusion? Oh, we see this a lot.
We do.
Yeah, we do.
All right. Those of you that are watching with us, if you'll type into the chat what you think is wrong with that one.
Oh, I'd be really, wish I could see that.
I know, I wish you could see that. Yeah. All right, Dennis says convincing evidence. Harrison says first, based on the data from the test.
Nice.
Okay. Nice. Okay. Micah says there's no alpha value.
Okay, all right.
To compare to the p-value.
That came first. Good point. Good point.
And then Katie says we have sufficient or insufficient evidence to fail to reject or to reject.
Yeah.
Okay.
Very good. Very good. Yeah, it's all about the data. Again, the way I phrase that, it's to what we call deterministic. Okay. The true proportion of students like these who would say yes to the question is greater than 0.5. Really? Really? You're certain of that? Yeah, not really. We still open it up to the possibility of a type 1 error. Yeah, so good. Yes, the data provide convincing evidence that the true proportion of students like these. So Good. We got a sharp group here. I like it. I like it. This is fun. And the last one, I'm going to buzz through this so we can move on. But I basically have the same error that occurs up there, only with a confidence interval. We are 95% confident that the interval 0.45 to 0.60 captures the true proportion of students who answered yes to the question. So it's really the same type of error that occurred up there using that past tense. I do tend to see that more often in confidence intervals, even with my own students, no matter how much I tell them. So anyway, nice job, everyone. Nice job with that one. So,
okay.
All right. Answer the question completely. All right. This is exam 2011 free response question number 3. And I think that this illustrates beautifully the answer the question completely. Now, a quick rundown of this question. What you see is a floor plan. It's an apartment. There are 9 floors. On each floor, there are 4 apartments. Some of the apartments are starred. They have children in the apartments. Now, the premise to this exercise is that the building owner is going to pick 8 apartments to receive new carpet. Yay! Wonderful. Who wouldn't want new carpet? But it's a little experiment, because what the building owner wants to find out is it wants to hold off on carpeting the whole darn building. It wants to see how well the carpet lasts over the years. Okay, so part B says, for convenience, the apartment building owner wants to use a cluster sample method in which the floors are clusters to select the 8 apartments. Now, we're not going to do this, but it is important that you know that a cluster sample was collected. So very briefly, randomly sample 2 of the floors, 2 of the 9 floors, okay, and then carpet all 4 apartments on the 2 chosen floors. And the installers are going to love you for that, okay, as opposed to randomly selecting 8 apartments. But yeah, that's a cluster sample. Now, I want to focus on part C. Part C. An alternate sampling method would be to select a stratified sample. And we talked about this earlier. Cluster sample versus stratified sample of 8 apartments where the strata are apartments with children and apartments with no children. All right? Now, you got to think, why is that important? We want to give one statistical advantage of selecting a stratified sample as opposed to a cluster sample of 8 apartments using the floors as clusters. All right. Now, I'm going to start this one off, and let's see if you can chime in and see why my answer is incomplete. My answer is very simple. Sure, with a stratified sample, okay, I am guaranteed picking apartments with children and without children because children are harder on carpets. I want to see how the carpets wear, okay, in apartments with children and without children. Okay? That's my answer. And I'm telling you right now, I get a P on that. It's not quite complete. Okay? Do you know what I left off? And it's subtle. It's subtle. This is what I mean by answer the question completely. Okay? Are we getting any responses, or did I stump them on this?
Let's see, you could pick 4 apartments with children and then 4 apartments without children.
Right.
So it's unfair if you do one group compared to the one. It's unfair if you do one group compared to the other.
Right. All right. I'm gonna spill it on this. Most students, when they talked about this, talked about stratified sampling, and that the stratified sampling will guarantee you getting apartments with children. And they explained why that's important. Children are rough on carpets. They'll grind their crayons and run their big wheels and throw up on the carpets and all that good stuff. Okay, but look carefully at the problem. In that last line, as opposed to a cluster sample. So, to get full credit, you have to talk about why a stratified sample is desirable and what's wrong with a cluster sample. So, I put it out there. What's wrong with a cluster sample? Why not? That's the last thing we have to address here. And my explanation did not address that.
Okay. All right. For inference procedures,
I'm sorry. No, did anybody chime in as to what was wrong with the
I'm so sorry. Did I move on? I'm so sorry.
That's all right.
Yes, cluster samples are based on confidence. Let me try that again. Cluster samples are based on convenience, so it may not be random.
Okay.
And some of the clusters may not be representative of the population.
Okay, that's close. That's closer, and that might even get you some credit there.
The cluster does not address that kids live in different areas.
Okay. They're getting closer. Think practical. Think practical. Look at those floors. Look at those floors.
I've got to get back to the floors.
Okay, that's okay. That's all right. I'll give the answer away here. Because with a cluster sample, it is possible to select 8 apartments with no children. Pick the 3rd floor and the 6th floor, or the 3rd floor and the 4th floor. Okay, yeah, the 3rd, the 3rd, the 4th, and the 6th floor do not have any children. So if you pick any 2 of those things, so there it is. Stratified sample guarantees you apartments with children. Cluster sample, it is possible to select 8 apartments with no children. So answer the question completely. That was tricky.
Yeah,
that was tricky.
A lot of hints in
2
there.
things in there at once. Yeah,
I'm not sure I would have got all 4 points on that one.
I play that game every year. Yeah, with myself, and like, wow, yeah, I have thought to do that.
All right,
through confession.
I'm going to move on to talking about inference. All right, we have about 20 minutes left. So knowing your inference procedures, you are going to see inference on one or both of your 2 questions.
100% guarantee.
Yep. So confidence intervals, know your steps. So some teachers call it panic. Other teachers call it the 4-step process, to where you state, plan, do, and conclude. But you have to state your parameter of what is it that we're trying to estimate at what confidence level. Confidence level is the percentage. So 95% is the confidence level. Name the appropriate inference procedure. Okay, we would prefer that you, for your own sake, is to write the name. So it is a 1 proportion Z interval, or it is a 2 sample T interval for means. You do not need to write the actual formula out if you just tell us what the name of the procedure is. Checking the conditions is huge. Huge that you go check those conditions. More on that in a moment.
About the 10% condition this year.
Yes, yes. James, are we going to talk about the conditions in a different slide, I'm thinking?
Yes.
Okay.
Yep.
Then, okay, when I get to this part, all right, if your conditions are met, then you go ahead and perform the calculations. Your calculations are going to be done for you this year, since it's basically, they're saying you can do the test without a calculator. And then very important is that you interpret what that interval represents in context. Okay. You always want to do that for a confidence interval. The extra, so only if you're asked, if the question says interpret the confidence level, then you would do, okay, tell us what 95% represents. If the question asks you to determine a sample size, so how big does N need to be for a specific margin of error? And that can be a little confusing if you have if you're using T when you have means. You're using means because it's quantitative data. Well, to find your sample size, you have to always go with Z, because that T depends on degrees of freedom, which depends on your N value. Whoops, I skipped over and I did not mean to do that. I am so sorry. I'm going
to make a speculation that, and again, this is just a speculation, that you're probably not going to see a sample size problem because that's a calculation. right? And they're going to keep the calculation light, but never say never. In other words, what Mrs. Knight is saying is be ready for any of these extras. They could come up.
That's right. One I could see them asking about is comment on the effect of changing your confidence level. So what would happen if you went from a 95% to a 99% level? What would happen if you changed the sample size on the margin of error? So asking about, is your interval, that's really asking, is your interval going to get wider? Is it going to get narrower? What's going to happen to the variability for a situation if you increased sample size? Okay.
I got one for them. Like, I could see them saying, what would happen to the margin of error if we increased the sample size by a factor of 4? Instead of n equals 100, it's n equals 400.
Yep. Yep.
Yeah. Should we put that out there? Should we put that out there? Let's see what they say.
What's going to happen if I sample from 100 and now I sample 400?
What happens to your margin of error?
Okay. Brandon, you're on top of this. All right. The margin of error reduces by the square root of 4.
Nice.
Okay. That is correct. Because you're really, if n was 100, you're going to multiply that by 4. But for margin of error, you're dividing by the square root of your n.
That's right.
So,
good. You could ask it in reverse. Approximately, by what factor do I have to increase the sample size to reduce the margin of error by a factor of 2 or 3? Yep.
Right.
Yep.
It is never.
Go ahead. Yep.
I was just going to say, whatever number they give you, so if you multiply by 4, it is never going to be, 4 is never going to be part of the answer.
Right.
So if they're saying, to split it in half, 2 is not going to be part of the answer. Okay. And then justify a claim based on a confidence interval. That would be similar to, okay, does 0 fall in my interval? That would be, okay, they claim the proportion is 0.5. Okay, well, does 0.5 fall in your interval? If it does, then we are supporting the claim. If it doesn't, then we are going to reject that claim. Okay.
All right.
And then test of significance. All right. You want to take this one, Mr. Bush?
Sure. I'm going to run down this very quickly. There's some other slides that we want to get to. Test of significance. Again, inference guaranteed on at least one of them. Could be both. So there's your 4-part scoring rubric for a test of significance. State the null and alternative hypotheses, and don't forget to define the parameters, and don't use that past tense like I did about 15 minutes ago. Name the appropriate inference procedures. You have 10 of them. There are 10 of them. Okay, you're not doing chi-square and you're not doing inference for regression. And check those conditions. Don't forget the 10% condition this year. All right, if the conditions are met, and they will be, perform the calculations, but as Mrs. Knight said, they will most likely be done for you. So once again, leveling the playing field, it's all the less you've got to do. And get your conclusion. We call it conclusion with linkage and context. Okay, because the p-value is less than any reasonable significance level, say 0.05, and these days they're having you specify the alpha value, we reject the null hypothesis. All right, so far I've got the linkage, I've got the conclusion, but I don't have the context. Now, as we talked about, the data support the claim that the true proportion of students like these who would say yes is blah, 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 blah. Okay. Here are your little extras. Be ready for them. Okay. Answer them only if you are asked. Please don't go on and on and on. If they don't want it, don't give it to them. Okay. Interpret the p-value. Yeah. Might have to interpret the p-value. Describe and provide a possible consequence of either a type 1 or a type 2 error. I've seen exams where they ask for both, okay, before the presenting the test statistic. And comment on the power the power. As the probability of a type 1 error increases, so does the power. As the probability of a type 2 error decreases, the power increases. As sample size increases, power increases. So all the little extras. All right.
Okay. Quick question on p-value.
Oh, wonderful. Wonderful.
Can you just talk about the interpretation of p-value real quickly?
Wonderful. Wonderful. All right. Let's see. I need a specific example. Let's go to that mythical one that I made up about. It was a questionnaire. Students answer the questionnaire, and we're testing whether the true proportion of students who would say yes is greater than 0.5. So it's a right tail test. Now let's say that the sample proportion was 0.6. Okay, that 60% of the students who were sampled said yes. All right, here would be my interpretation of the p-value. All right, assuming that the null hypothesis is true, but in context, assuming that the true proportion of students who would say yes is 0.5, there is and I'd have to fill in the p-value, maybe it's 0.0423 chance of observing a sample proportion greater than or equal to 60%, 0.6, by chance alone in a random sample of however many there were. So, thank you for asking. It's not an easy thing to answer orally. Right. So I would say, please consult with your teacher about a good template to use, and consult with your textbook. If you are using TPS, the practice of statistics, there's a lot of really good examples and a good template to use for interpreting p-value. Yeah, thanks for asking that. I would not be surprised at all if that rears its ugly head.
Correct. Yep. That is a common one, isn't it?
Yes. All right. Our next section here, and we're going to speed things up slightly. I call it know the what's, the whys, and the hows. Okay, the what's, the whys, and the hows. So with this one, I'm going to direct you, and they're all online. They're all online. It was exam 2017, free response question number 1, which threw us all for a loop when we saw that one. It was a routine, it looked like a routine regression problem, but they wanted us to explain, wanted the students to explain what is meant by a positive and a linear and a strong relation. What do we mean by that? Now, there were a lot of different ways of answering those. There's a lot of different ways. My question team was actually on my table. My reading table was actually assigned to that question, and it was a bit of a difficult read. But here you have some model responses on what it is we mean by positive, what is it we mean by linear, what is it we mean by strong. Positive relation means that wolves with higher values tend also to have higher weights. Oh, higher, well, just when I think I got all the typos out of it, it would be a higher length, nose to tip of tail, also tend to have higher weights. So that was an omission on my part. Linear, if you read that, that is roughly the interpretation of a slope without actually being provided with a slope. And there was a lot of ways of answering strong, but one is that the data points fall close to the line or the curve. You can have a strong relation and not a linear. So I would invite you to take a look at exam 2017 free response question 1. Yep. And I think with that, we'll move on. So Karen, I want to take the next one here. Talking about the advantage of stratified sampling compared to simple random sampling. Yeah. All right. What is the advantage? Oh. All
right, let's ask the kiddos. What do y'all think an advantage of a simple random sample, stratified over a simple random? What do y'all think? Now, in my class, they better know that simple random sample, we basically can do that 3 ways. It's the hat method. Put everything in a hat, mix them up well, and then start drawing names. It is the random number digit table, because we all carry one of those around in our pocket, or it's random number generator, like the calculator, or you go get numbers off the computer, something like that. Those are the only three ways for an SRS. All right, so Katie says Stratify ensures that all groups of strata are equally chosen. And why is that important? Why would that be important? Okay, Eric says Stratified guarantees it includes certain groups versus you could inadvertently not include a certain group, like a grade, like the 9th grade could inadvertently, just by random sampling, be left out. So yes, you want to make sure that you are representing the population by taking some from all of your groups for Stratified. You want some from all.
Okay, I want you all to know that response right there. Okay, it appears in textbooks.
Mm-hmm.
You may or may not know this, but a stratified random sample gives a more precise estimate. Okay, estimate of a population mean. Okay, more precise than would be obtained with simple random samples of the same size. Yeah, it actually reduces. There are special formulas. They're higher level things, but there are special formulas for a standard deviation obtained from a stratified sample. But yeah, it actually reduces the standard deviation of the sample mean. So I'd like you to know that. Never know what's going to come up.
Never know.
Yeah.
All right. Box plot.
Oh, yeah. Now
we
we touched on this
minutes.
earlier. Okay. And I put an awful lot of work into these three. So watch this. I mean, here you have 3 symmetric box plots. Okay. What can you tell? Somebody asked this earlier. It was a great question. Okay. All I can tell, the best I can tell, is the shape is symmetric. Can we tell normal? Yeah, no. No. And if you'll hit the next slide, you're going to see that the top one, right? Yay, spent an awful lot of time on that one. Look at that. The top one comes from a bimodal distribution. See little peaks there? See a little? The middle one I designed to come from an approximately roughly uniform, see, roughly uniform. And the last one is about, that's supposedly the normal one, or as close to normal as you're going to get. So, wow, could you tell? I'll bet if you saw the 3 dot plots, okay, and were asked to match them with the box plots, I'll bet you could do it. Yeah, I'll easily bet all of our viewers could do that. But no, telling one, which one's the normal one? No, can't tell. Can't tell.
So one of the questions on here was, what can you tell? And over in the chat, they're telling us you can tell if there's outliers. You can tell what Q1, Q3, and the median are, and then find the IQR from that.
Oh, I've got a question for them. Let's pitch this. Can I tell the mean from these box plots? These box plots.
Right. Dahlia's already on it, and they're saying no. She said that immediately. You cannot tell what the mean is. Good job.
Can I approximate the mean from these box plots?
They're saying the mean equals the median because it is symmetric.
That's where I was going with it.
Yeah.
So the answer is yes. From these box plots, which are symmetric, I can say that the mean is approximately the median, which is true for a symmetric distribution. So for these box plots, for a box plot in general, no. Good one. Good. This is fun.
All right.
All right.
Experimental design. Why in the world would we block? Well, the one that we talked about earlier was experiment to determine whether oil type affects the car's engine. So we chatted about this and explain why randomized block design might be preferable to a completely randomized design. So there's one of those that you really have to read, and I could see them asking something like this. Since numbers are not going to be a big part, explaining is. So explain why the randomized block, oh my goodness, I keep clicking the wrong thing. Explain why the randomized block design might be preferable to the completely randomized. A good response. The randomized block design accounts for the variability in the engine life created by the different engine sizes, which makes it easier to determine whether oil type affects the car's engine life than if a completely randomized.
Then if a, thank you. Then if a.
Yes, a completely randomized design. Correct.
Yeah, folks, I want you to know that response there. I want you to review that response. You know, why exactly do we block? I think that's going to be the secret to this year's exams. You got to know the hows, the whys, and the whats. And the slide I really want to get to, we got 5 minutes left, but this next slide is the one I really, really, really want to get to because I think that this is going to be on. Okay, the conditions. Let's just right now talk about the conditions for a mean, okay, inference for a mean, a single mean, a random condition.
So we're talking about those conditions that go with intervals, confidence intervals, and hypothesis tests.
Thank you, thank you. I'm so excited to get to my point.
I know.
Wonderful. Yes, the random condition, the 10% condition, the normality, or large sample conditions, why are they there? Why are they there? Well, it's all connected to the sampling distribution. And I want you to think about the 3 key characteristics of any distribution. Go back to your basics: shape, center, spread. Shape, center, spread. All right? And I outlined it. The shape, okay, covered by the normality or the large sample condition. Center, covered by the random condition. Spread, covered by the 10% condition. Very briefly, okay? The center, random, a random sample. Okay, if the data is not obtained from a random sample, then X bar, okay, will no longer be an unbiased estimator of mu, and that affects the center, unbiasedness. The center is where it is supposed to be. So that you need that for the center of the sampling distribution to be where it's going to be. The 10% condition, okay? Basically, the bottom line is, you see that formula right there? You should be familiar with that. Sigma over root n. Yeah, if the 10% condition is not met, that formula does not hold true. It does not. It's a different formula. You have to use what's called the finite population correction factor. We're not going to go there, but there's spread. And the last one, normality or large sample. If the sample size is small, you've got to assume that you're selecting, you're sampling from a normally distributed population or an approximately normal. Sure, you sample from a normal distribution, X bar is going to be approximately normal. That makes sense. But if it's not normally distributed, you have to check to make sure your sample size is large. Now, this is the amazing central limit theorem, which is very powerful. You say, wow, if the sample size is large, you don't have to worry about the distribution of what I call the parent population or the sampled population. Central limit theorem has you covered. Central limit theorem says that the sampling distribution of X bar is going to be approximately normal, regardless of the distribution of the sampled population. So I want you to review that slide. Shape, center, spread. That's why we need to check those conditions. Be ready for that one.
Absolutely. Absolutely.
All right.
Okay, well, and always use context.
Yeah. Yeah, we're heading into our last several minutes. These are pretty easy. How do you compare 2 or more distributions? I would think that the majority of our viewing audience knows all about this. You want to compare shape, center, spread. You want to use comparative language. Yeah, let's oh, Karen, let's get to the one that you proposed. Oh, the probability one. Yeah.
Okay. Here we go.
Yeah, you and I both think that this is, that one. Yeah. That one. Yep.
Okay, asking about, I would be ready for a question that is asking you about, are these 2 events independent?
Yeah.
Independent. Okay, so this is when on your formula sheet, which I would have a copy of that in front of you on test day, go ahead and get it ready, print it out, have it next to you. So on your formula sheet, they're independent events if the probability of A given B equals the probability of A. Actually, I don't think that's on their formula sheet, is it? Now that I say that, the given formula is.
I don't think it is.
Right, the given part is. So knowing if two events are independent, and how do you show if they are or if they are not? Okay. Let's see. Do you want to go ahead and answer that part for me,
Sure.
Mr. Bush?
Sure. This problem actually took you through the first several parts. So you calculate the probability of never, or that's shorthand for never taken the medication. Okay, and that's a marginal probability. It's technically is 0.12 divided by 0.1. If they were counts, you'd have to do a little division there. As I say, we're thinking that this is going to be on there because this is pretty easy arithmetic. Okay, and then you calculate the probability, the conditional probability of never, given that the respondent is a woman. The person surveyed is a woman, and that was 0.0636, and that's the probability of never and woman divided by the probability that a woman was selected. And that happens to be also 0.12. Wow, they are the same. Usually it's the other way. Usually they're different. This one surprised me. Yeah, it's like, oh, wow, this year they made them the same. Okay. And there are several definitions of independence, but the one I like is that two events A and B are independent if the probability of A given B, the conditional probability of A given B, is the same as the unconditional probability of A. In other words, B doesn't matter. Knowledge of B does not alter the probability of A. Okay, and they're the same. And that's all you have to say. And I like my use of the word because. That's your best friend, which is actually our last remaining slide. What happens at 5 o'clock? Are we like shoved off of this thing, or can we keep going? I don't know. Let's keep on going.
Yes.
If we're tossed off, we're tossed off.
Okay.
Yeah, we're owed a couple of minutes anyway because of that glitch there. So, all right. So, because, and this is our last tip, because is your new best friend. Absolutely. Because strengthens your argument. Especially use the word because, or its lovely little cousin since. Since is a nice word too. Okay, it strengthens your argument and it helps you establish connection. It improves overall communication. Did you see how I used it in the last one? Because this is true, this the relationship between the probabilities, we have independence. Here's a test of significance. Because the p-value is less than any reasonable significance level, the null hypothesis is rejected, and the data support the claim that the true mean height of all students at Pleasantville High School is more than 68 inches, and I just made that up. So, but put that word because in there. It's your new best friend, at least between now and May 22nd. And let's see, the next one, I think it's our last little slide there.
Sorry, I'm going back and forth to answering questions. Okay.
Oh, no, go ahead, please, yeah.
All right, you're good.
Okay. And addressing bias. Be ready to do this too. Our last little example with regards to bias, the marketing manager of a professional soccer team wants to estimate the true mean income of the fans that attend their games. What's the manager going to do? They're going to ask 50 people who are seated right in back of the team's bench for their annual income. All right. And the mean response from the members was $89,162. Okay. This is suffering from under coverage, because if that was their sampling plan, then the people in the cheap seats had no prayer of being selected. But here I'm using the word because to strengthen my argument. Because seats behind the team's bench are very expensive, the 50 fans sitting in these seats probably make more money than the fans sitting in other sections of the stadium, leading to an overestimate of the true mean income of all fans of the game. Okay, and the other takeaway, okay, and Karen, as you and I were prepping, you pointed this out. Okay, always address the direction of the bias. Okay, leading to an overestimate. Okay, you're not going to get full credit if you don't address, is it an overestimate or an underestimate? Yeah, gotta address the direction of the bias. Let's toss it over to our students and see if they have any final questions, because I'm out of stuff.
They have been asking some great questions over here, just kind of about just ins and outs a little bit. Oh, I didn't stop sharing. Okay. So things about, okay, what type of paper? It does need to be white paper. It doesn't matter if it's lined or not lined. I answered over there that you may upload one PDF. So if you're going to scan using your phone, then it needs to be, you can scan 5 pages, but it can only be uploaded as one PDF, not 5 separate PDFs. If you're going to take a picture with your phone and now it's going to be a JPEG, that is going to be, you can have 5 separate JPEGs.
Wow, good question. Getting along technical.
You need to, when you upload, I've done some in the AP demo part, so I highly recommend that you practice in the AP demo and see what do you like better. Earlier, somebody had said, do I recommend writing or doing it on your Word document? I'm going to say it's up to you. I personally would have to write it all down. I'm better on paper than I am on technology, but you younger folks might be better on the technology part. My classroom has not typed all of their stat stuff on the screen all year, so I don't really want them to be starting that now. But you can upload, and if you're whatever you're uploading, you need to, if you email it to yourself, you need to save it to your desktop. You need to open that up on your desktop to make sure it is rotated the correct way before you upload to the College Board website. So you don't want to upload something that is sideways. We can't read like that.
Yes, both of us, by the way, will be readers. Both of us will be readers. So yeah, thank you, because I don't want to turn I'll have a laptop, so I suppose I can turn it that way. But
and Mr. Bish was talking about, we're mentioning independence with probability. Each question 1, question 2, are independent of each other. So I know when you turn papers in to your teachers in class, you're turning in, here's my questions 1 through 5. Here's, can you grade them now? Each one of these is going to be independent. So you will not have, I can promise, I will not grade both of your questions. There's no grader that will grade both of your questions.
Nope.
So numbering your pages 1, 2, 3, 4, 5, and you don't need to go now 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Because your questions are going to be separated into little, however they do it in the cloud.
Right. And as long as we're talking about this, of course, each question is going to have multiple parts on it, A, B, C, D, okay, maybe an E. Yeah. Don't assume like, oh my gosh, I can't do part B, so I guess I'm not going to be able to answer part C. No. Go on to part C, go on to part D, okay, because they could be totally different things being asked. Yeah, don't do that. Attack everything. Okay,
if it's a probability or any type of question, if you know you could do part C, but you needed the answer from part B to do part C, make up a valid answer. I was grading a paper a couple years ago, and the kids would make up a probability value. And if they just made one up and it was realistic, they didn't get credit for making it up, but they got credit for using it in the rest of the problem. However, some of them made up a number and their probability was 2.5. That's not a valid probability. Probability is only between 0 and 1. Yeah. Okay. You could have had 2.5%, but they didn't do it that way. So as long as it is a valid value for that particular question, then you can make up a number.
That's good. All right.
Any other questions y'all want to send in the chat? I appreciate y'all being, I'm missing some. Okay, let's see. Take a picture with a pen and pencil and see if you can read it. Oh, I read that wrong. Take a picture with your pen or pencil and see if you can read it. Okay. If you're using Cam Scanner, the pencil doesn't really show up well. Okay, for the, let's see, 10% test, is that trying to say that our sample is less than 10% of the population? Yes. Correct. There are no requirements that you have to use a pen.
Nope.
Should we make sure we know how to transform data from linear to exponential in Power Model by hand? No.
Nope. Guaranteed.
No.
No. Yeah.
You're off the hook. By calculator? No.
Nope.
The only thing you would need your calculator for is if you wanted to,
Simple
I don't know,
arithmetic.
divide 54 divided by 76 and write a decimal.
Right.
But you could leave it 54 divided by 76.
Yeah. Probability, numerator, denominator, leave it.
You should be able to work the whole test without a calculator.
Yeah.
To keep the playing field even.
I'm going to take this opportunity before we leave for a couple of personal shout outs, especially if anybody in New York City is watching. I've done a lot of work at the study sessions in New York City. Miss you guys, love you guys, students, teachers alike. Really good luck. And anybody in the Pittsburgh area. Don't know if any of Mike Lacey's students are watching, or June Bigley down there in Kappa. A lot of good, talented AP statistics teachers here in the Pittsburgh area.
Awesome. Katie says she's from the East Coast family. So,
nice.
Awesome. All right. Well, we appreciate you guys being with us today.
Thank you for sharing a Saturday afternoon, depending on your time zone.
I know. Some of you, it's dinner time. So,
yeah.
All right. Thank you, guys. We appreciate you. And we know that you're going to do fantastic on the 22nd.
We do. We do. As I said, please remember what we said. You know, you really have a good chance this year at
the odds are in your favor. That's right.
Yeah.
Okay. Thank you.